Let me start with a question. Suppose you just add a const keyword to a variable or a function parameter in a piece of C++ code. Would you think it affects performance? Most people would say probably not. Const only restricts modification. It doesn't add any extra operations. But the reality is that in many engineering projects, a single const change can directly tank performance. What's worse, the code compiles without errors, the logic works perfectly fine, and only a profiler can catch this hidden performance killer. In today's video, I want to make one thing crystal clear. In C++, const is not just a read-only marker. It's a design decision that can alter the entire performance path of your code. Let's start with a very real engineering scenario. Numerous libraries and projects use function overloading like this. The original design intent is straightforward. For non-const reference parameters, the function can modify the past object directly without extra copying, achieving maximum efficiency. For const reference parameters, it promises not to modify the past object, ensuring data safety for the caller. Now look at the code below. When it runs, everything works smoothly. The compiler will match the non-const version and take the efficient fast path. But if you add a const keyword to the variable during refactoring, the code still compiles without issues and the logic seems unchanged. However, it has silently switched the execution path. Now it calls the const version. To guarantee safety, the const version often triggers a defensive copy. What does that mean? If the function needs to temporarily modify data internally, it has to create a copy of the past object and modify the copy instead of the original. This copy operation can lead to additional memory allocation and data duplication. Especially when data is a large object, the overhead becomes extremely noticeable. This kind of performance regression is extremely common in large-scale projects. And during code reviews, who can spot the overloading switch hidden behind a single const keyword at a glance? If the pitfall of overloading switching can still be detected through code reviews, the next issue is even more insidious. Many high-performance codes rely on black magic optimizations, such as lazy loading, internal catching, and lazy evaluation. For example, a compute-intensive class might be designed with a member function like this. The essence of this design is to perform the calculation only once and reuse the result in subsequent calls, resulting in significant performance gains. But if you change this function to a const member function, trouble arises. C++ rules stipulate that const member functions cannot modify non-mutable member variables. This means variables like result and isCalculated cannot be modified at all inside the const function, rendering the catching strategy completely ineffective. Is there a way to fix this? Yes, you can use the mutable keyword directly. But here's the catch. In many team coding standards, mutable is regarded as a dangerous keyword. Its usage is either strictly restricted or outright forbidden. As a result, you have to abandon catching and re-execute the time-consuming calculation every time the value function is called, leading to an immediate and drastic drop in performance. This is why I emphasize that const is an API promise, not syntactic sugar. Adding const to a member function is equivalent to promising the compiler this function will not change the logical state of the object, and at the same time, you give up optimization methods that rely on state modification. There's another little-known fact, which is the most easily overlooked and also the most performance-impacting. Const directly blocks move semantics. Let's look at a piece of code first. In C++ 11 and later versions, this code triggers the move constructor, which directly hijacks the resources of the temporary object returned by the getData function with almost zero overhead. This is what we call a cheap move. But if you think adding const makes it safer and rewrite it like this, logically it seems exactly the same, right? But the performance is worlds apart. The core of move semantics is modifying the source object after transferring the source object's resources to the new object. The source object becomes an empty shell. However, the core property of a const object is immutability. The compiler cannot perform a move operation on a const object at all. It has to settle for the copy constructor instead, duplicating all the data of the source object. This is an expensive copy. This scenario is particularly common in places like STL containers, lambda captures, return value forwarding, and intermediate variables. The scariest part is that you don't write a single copy keyword in your code, but the copy operation actually happens, and it's extremely hard to detect. Let's take another common pitfall, const containers. For example, you have a regular vector. You can sort it, swap its contents, expand its capacity, and STL algorithms will apply various in-place optimizations to it. But if you add const to it, you might only intend to express this vector should not be modified, but you end up locking down far more than that. You cannot move elements inside the container. You cannot call efficient modification operations like swap. Many STL algorithms have to abandon in-place optimization and instead copy elements to a temporary container for processing. The compiler loses the ability to optimize the container's memory layout and has to take the most conservative execution path. This is why the performance models of many STL algorithms are completely different between const and non-const containers. At this point, some of you might be thinking, why not just stop using const altogether? Of course not. const is one of the most powerful features in C++. It clarifies API semantics, prevents accidental data modification, and improves code readability and maintainability. The real engineering takeaway is use const at the boundaries, not in internal workflows. Here are 3 key takeaways for you. First, always use const in public interfaces. For publicly exposed function parameters and member functions, add const whenever possible. Just like the code shown on the screen, this conveys clear semantic promises to callers and is a basic skill for professional developers. Second, use const cautiously in internal implementations. For internal temporary variables, function parameters, and member functions, don't blindly add const just for the sake of seeming safe. The core goals of internal code are performance and flexibility. Overusing const will restrict optimization opportunities. Third, clearly distinguish between move and copy in performance-critical paths. In high-frequency call scenarios and when handling large objects, always clarify the mutability of variables. Variables that need to be moved should never be marked as const. Meanwhile, use mutable appropriately to retain optimization techniques like caching. Finally, remember this. What const changes is not whether you can modify data, it's whether the compiler can still help you save work. Alright, that wraps up today's discussion on const in performance. If you've ever fallen into a const-related pitfall or have other C++ performance optimization experiences to share, feel free to leave a comment below. Like and subscribe, and we'll see you in the next video.